your presentation.
I'm Sean Okamura.
I'm Gavin Choi, and this is our presentation on the derivation of the inertia of a sphere. Alright, so first we can see here that we have a sphere. We have the equation for the volume, and what we're going to be doing here is we're going to be trying to find the area of the sphere. So we do this by doing what we learned in class, where we take an infinite number of cylinders. So we're doing this cylindrical shell to to find the area. And if we scroll down, here we can see that being done. Scroll down.
You're not gonna break it down.
What?
The whole point did the calculations for you to go over
I
this.
mean,
What's the point of proving
the numbers
it?
are just there, man.
Well, maybe say a few words about it.
Okay, scroll up.
Okay, I'll do it.
Bro, what do you want me to say? It's just the.
Okay. So to break it down, you have to take an infinite amount of disks for the sphere. So the way I did it is by taking the radius of this the first disk, which is r, and then the x-axis, and then big R, to get the Pythagorean theorem to substitute for r. Now we need this to substitute into the original volume formula to cancel out the r, and then we can take the derivative of it, giving us the derivative of volume times pi times r squared dh, and then we can sub it into dv pi big R squared minus x squared dx, and that gets us to dx. From there, we have to use density because we're trying to get the moment of inertia. Let's go up a bit. So we have rho times the mass times the volume. Then we can take that apart to get mass equals rho volume. And then we need the mass because if anyone knows the original inertia equation, mass is a factor of it. So we want mass to be part of inertia just because it's the how to explain? It's the rate an object does not want to move, and weight is a factor, a part of that, so we need mass. So we take the derivative of that, so we get dm equals rho dv. Now we have our original equation, which is dv, so then we can sub it in to get dx into our equation. Then we will have dm equals rho pi times r squared minus x squared dx. Then we want to sub in for inertia. So we get inertia is, well, this is the original inertia equation that you sub it into to get inertia. Well, the mass is there, you sub in both equations. So you get inertia is a rho pi over 2 times the whole thing. Then you have to take the integral because we took the derivative of it. We have to get back to the original step. So we take the integral of the whole equation. And then that gets us to inertia, but then we still have to take the integral of this. Now, down here, the reason why we take the integral from negative r to r is because it's a circle, and assuming that the circle is, well, it's a circle and the radius is half of it, so we do from negative r to r, assuming that it's at the origin a 0. So that gets us the integral from r to r, which should encompass the whole circle, which is right here. And this is just all the steps I did to integrate all of it. I just multiplied it out. I squared the entire thing. And because this is the even odd, because the function is even and odd, it kind of cancels out nicely. This is just all the steps. If you decide to make it r to 0 minus 0 to negative r, it all cancels out, and because it's an even function, these two just cancel. There's all the steps. And here we have rho pi r5. With all of this, I did the common denominator, got 8 to the 15th. and then I subbed it all back into the original function. This is still equal to velocity. We did dv. So when you sub it back in, you get back to the mass equals what is it? Rho 4/3. And then you can sub it back into the original inertia equation, which is right here, and that gets the final inertia equation. And then that's the derivation of a sphere. Any questions?